Ever wondered how farmers are optimizing their fields with cutting-edge tech? Today we're diving deep into the Leaf Chlorophyll Index, or LCI, a game-changer in precision agriculture that's transforming how we monitor crop health from sprawling orchards to vast rice fields. We'll explore the science behind LCI, how it's used with drones and satellites, and why it's becoming an indispensable tool for maximizing yield and sustainability. Before we get into LCI, let's talk about chlorophyll. You know, the green stuff in plants, but it's so much more than just color. Chlorophyll is the engine of photosynthesis, converting sunlight into energy. Think of it as the plant's solar panel. Its concentration isn't just about how green a leaf looks, it's a direct indicator of the plant's overall health and, crucially, its nitrogen status. Nitrogen is a key component of chlorophyll, so a plant struggling with nitrogen will show lower chlorophyll levels, often turning yellow. This gives us an early warning system, and here's the cool part, we can detect these changes from a distance. How do we see chlorophyll from above? It's all about how plants interact with light, specifically their spectral signature. Healthy green plants absorb a lot of blue and red light for photosynthesis, but reflect a lot of green light. That's why they look green to us. But the real magic happens in the near-infrared NIR spectrum. Healthy plants reflect a lot of NIR light due to their internal cell structure. Now pay close attention to the red edge. This is the sharp transition zone between the red and NIR spectrum. It's incredibly sensitive to chlorophyll content. As chlorophyll increases, this red edge shifts. This subtle but critical shift is what indices like LCI leverage to give us detailed insights into plant health. So what is the Leaf Chlorophyll Index? Well, it's not just one formula. The term LCI can refer to several calculations, but they all aim to estimate chlorophyll content using specific light bands, especially the red edge. Let's compare LCI to some other popular indices. NDVI, Normalized Difference Vegetation Index. This has been the standard for decades using red and NIR bands. It's great for general plant vigor and biomass. However, NDVI has a big limitation. It saturates in dense, healthy canopies. It can't tell the difference between a really healthy crop and a slightly less healthy one once the field is fully green. LCI, NDRE, Normalized Difference Red Edge. This is where LCI shines. It uses the red edge band instead of the red band, because red edge light penetrates deeper into the canopy and isn't absorbed as strongly as red light. LCI NDRE stays sensitive even in dense canopies. This means it can detect subtle changes in chlorophyll and nitrogen status when NDVI has maxed out. This is crucial for late-season management and precision nutrient application. There are other chlorophyll-sensitive indices too, like Green Chlorophyll Index, GCI, and Marist Terrestrial Chlorophyll Index, MTCI, each with unique strengths. Let's see LCI in action, starting with high-value orchards. Managing fruit trees is tricky. Too much nitrogen can hurt fruit quality, but too little affects growth. LCI helps growers move from guesswork to precision. By monitoring LCI maps, they can identify specific trees or zones needing more or less nitrogen, leading to variable rate fertilization. This ensures optimal growth without compromising fruit color, firmness, or storage potential. LCI can also detect early signs of stress, whether it's from water shortages, pests, or disease, often before visible symptoms appear. This allows for targeted interventions, reducing waste and minimizing the spread of problems. A key challenge in orchards is their complex 3D structure. But with high-resolution drone imagery and advanced processing, we can do per-tree analysis. This means LCI is calculated for each individual tree, giving growers incredibly detailed insights. Now let's talk about rice, a staple for half the world's population. Nitrogen use efficiency, NUE, is a huge challenge in rice farming, with much of the applied nitrogen being lost. LCI is a game-changer here too. Because chlorophyll content is directly linked to nitrogen, LCI acts as a real-time proxy for the plant's nitrogen needs. Farmers can use LCI maps from satellites or drones to apply fertilizer precisely when and where it's needed, significantly improving NUE, reducing costs, and minimizing environmental impact. Beyond nutrient management, LCI is proving to be a powerful tool for yield prediction in rice. Studies show that LCI, especially when tracked over time during critical growth stages, can accurately predict final yield and components like grain number. This temporal analysis, often using advanced machine learning models, allows farmers to make more informed decisions throughout the season, leading to better yield outcomes. So how do we get this LCI data? It comes from a combination of platforms, satellites. Missions like Sentinel-2 are crucial. Sentinel-2 from the European Space Agency offers free, open data with multiple red edge bands and a frequent revisit time, making it ideal for large-scale monitoring. Commercial satellites offer even higher resolution. UAVs, drones. Drones are a game-changer for precision agriculture. They offer ultra-high resolution, centimeter level, and incredible flexibility, allowing farmers to capture data on demand, even below cloud cover. Popular drone sensors like the DJI Phantom 4 multispectral or MicaSense Red Edge M are equipped with the necessary red edge bands. Ground-based sensors. Crucially, remote sensing data needs to be validated. Handheld chlorophyll meters like the SPAD 502 are essential for ground truthing. These provide direct in-field measurements that help calibrate and confirm the accuracy of the satellite or drone data. The most effective approach is often a hybrid. Use satellites for broad monitoring, drones for detailed problem areas, and ground sensors for validation. While LCI is powerful, it's not without challenges. Factors like canopy structure, soil background, and atmospheric conditions can influence the signal. Also, models developed in one location with a specific sensor might not directly apply to another. This means local calibration and validation are key, but the future is incredibly exciting. Researchers are developing more sophisticated indices that are less affected by these confounding factors. We're moving towards multi-sensor data fusion, combining LCI with thermal data, LiDAR for 3D structure, and even radar for a comprehensive view. 3D canopy chlorophyll mapping. Advanced 3D models of chlorophyll distribution within the canopy, enabling even more precise management. The leaf chlorophyll index is transforming agriculture, empowering farmers to make smarter, more sustainable decisions. The future of crop monitoring is here.